Hello, hello, hello. In this worked example called Speedtrap, we're going to take a problem that's done in Wolfson. It's example 2.4 in my edition of Wolfson. And we're going to give an alternative way of working on this problem, showing how VPython can be used to analyze this situation and do some things that you can't do with a pencil and paper. We can get a real-time animation of the story that's going on here. And not only that, but I'll show you how to use VPython to generate a real-time graph of what is going on in the story. So the speed trap story is a speeding motorist zooms uh, through a 50 kilometer per hour zone. That's about 25 miles an hour. No, I'm sorry, 30 miles an hour. And she's doing 75 kilometers an hour, so she's 50% over the speed limit. And that's a speed in SI units of 21 meters per second, and she doesn't notice a stationary police car. The police car immediately heads after the speeder, accelerating at 2.5 meters per second squared. And then the question we want to answer is, when the officer catches up to the speeder, how far down the road are they both, and how fast is the police car going when she catches up to the speeder? Now, if you read through the Wolfson example, there's a perfectly fine analytical solution to this problem. You can write down equations of motion for both the speeding car and the cop car. And, it goes something like this. The x coordinate of the speeding car, we'll call that x car, uh, is given by the speed of the car, velocity of the car, times time. So this is the x coordinate of the car as a function of time is just the velocity times time. And we'll assume that the origin of the coordinate system is located at the place where the speeding car passes the initially stationary police officer. And then the x coordinate of the cop, we'll call x cop as a function of time. That's just given by 1/2 the acceleration of the cop times time squared. And you could read through the Wolfson example, and he shows how to use these equations of motion to answer the questions that are being asked here. So what we'd like to do in this worked example is to provide an alternative approach showing you how you can use numerical methods in VPython to analyze and produce real-time animation and graphs of what is going on in the story. So let's dig in.
Okay, so let's see how we can use VPython to both animate this story of the speeding motorist, the speed trap story, and also make a real-time graph of the motion, which are two nice things you can do with VPython. And we're going to use our standard Euler's method to make the animation. So we're going to start off with this template here, in which I filled in a lot of the sort of background details that you need to get going. There's a lot of stuff here. You don't have to worry about all the details here, but this beginning part sets the scene about how big the screen is going to be, where the origin is going to be placed. We're going to place it on the left edge of the screen, and we're going to set things up so that the car and the motorcycle that the cop drives are going to be traveling in the horizontal direction. And we're also going to put on the screen a horizontal line of 500 meters in length, just to sort of set the scale so that we can sort of see what the distance scale is on the screen. And then all this stuff here has to do with setting things up so that we can make a position versus time graph right below the window where the animation is playing out. And for starters, let's just worry about the car. We'll add the cop's motorcycle in a little bit, but we're going to create a spherical car that'll be red in color, and we're going to have it leave a trail behind of these Hansel and Gretel like breadcrumbs, so that we can sort of see how its motion is progressing. And we'll set the car to be initially at the origin of our coordinate system, which I said is going to be on the left side of the screen. And then we want to set things up so that we have a main loop which runs for 20 seconds. So we set time initially to 0. We pick a time step. We'll pick it to be 1/10 of a second. And the animation is going to run as long as time is less than 20. And in this main loop, each time we go through the loop, we're going to increment time by a time step. So we're going to run for 20 seconds, and having this line at the beginning that says rate 1 over parentheses 1 over dt, that's going to cause the animation to run in real time. And right now, the only other thing we're going to put in the main loop is a request that each time we pass through the loop, we update the plot that we're going to be drawing, this position versus time graph of the car's position versus time. So if we run the program as it stands now, not much is going to happen because we are not updating the car's position. The car just stays at the origin, and this position versus time graph is playing out, and we see that over the course of 20 seconds, the car's position remains at a horizontal with an x coordinate of 0. Okay, so to make the car move, all we've got to do is to add in the main loop a request to update the car's position. And in order to do that, we're going to set the car's position equal to the car.pos plus the car's velocity, which I'll call vcar, times the time step. That is updating the car's position, like so. Now, in order for this to work, we have to tell VPython what the car's velocity is. So vcar, we're given in the problem, velocity, of course, is a vector. So we make the car's velocity a vector, and it has a velocity of 21 meters per second in the horizontal direction. So we give the x component of the velocity a value of 21, and the y and the z components velocities of components of 0. And we don't have to update the car's velocity in our main loop because this car is traveling with a constant velocity. So now when we run the program, what happens? We see the car moving along steadily, leaving a trail of equally spaced breadcrumbs behind, and we see our position versus time graph. We're plotting the x component of the car's position versus time, and that is increasing linearly throughout the 20-second interval, and we end up with a final x position of 426 meters. This little cursor here tells us what the final position is, and that makes sense because we said this white line here was 500 meters long, and we made it a little bit more than 4/5 of the way along the course here. Okay, so far so good. Now, what do we have to do? We have to add the something about the cop and her motorcycle. So to do that, I'm going to just copy this code that we used to create the car. And now we'll call this new object the cop. And we're going to make the cop green. And what else? We need to give the cop an initial position. So I'm going to make the initial position of the cop also at the origin. And now for the I want the cop to also leave the trail that she leaves behind. Let's make that green as well. Okay. And now in our main loop, oh, and we also have to, what else do we have to do about the cop? We have to say what the cop's initial velocity is. So a v cop is equal to, again, it's a vector, and the cop is initially stationary. And I want to make this a lowercase v because everything here is case sensitive. And now the cop is also going to be accelerating. So the acceleration of the cop we'll call a cop, and that's also a vector quantity. And the problem tells us that the cop is going to have a horizontally directed acceleration of 2.5 meters per second squared. Okay. So now in the main loop, I want to deal with the cop. So I have to, first of all, the cop's velocity is going to be changing. So I have to update each time through the loop the velocity of the cop. So the velocity of the cop, the new velocity of the cop is equal to the old velocity of the cop plus the acceleration of the cop times dt. So that is updating the cop's velocity. And I also have to update the cop's position. So cop.pos is equal to cop.pos plus the velocity of the cop times the time step. And that is update cop's position, like so. Okay. And one last thing, I want to create on the same plot, I want to graph the cop's, position. So I'm going to have this line that says cop curve here, and I'm going to plot the cop's position. And in order to get that to work, I also need to add a line here that defines what we mean by cop curve. So I'm going to have the cop's curve be green to match the color of her car, of her motorcycle. So that's a green curve for the cop. Okay, I think we're all set. We'll find out when we run it. Let's find out. So there's the cop in the car, and the cop is catching up. You can see the green curve, the slope is increasing because the cop is accelerating. And there goes the cop catching the car and going through. That's pretty good. Now, it's a little bit annoying that the breadcrumbs that are being left behind are overlapping. It makes it a little bit hard to see what's going on. So let's fix that. Let's go back to the beginning of the program, and I'm going to make the cop. I'm going to make the cop's initial position. I'm going to put it a little bit lower on the screen. I'm going to make it maybe 25 meters below the car. So now when we run things, the cop is still going to move horizontally, but now when we run things, we'll be able to see the breadcrumbs that the cop is leaving behind a little bit more clearly. And here you can see that the spacing between the cop's breadcrumbs are getting larger and larger because the cop is accelerating, and we can see the curve of the cop catching up with the curve of the car. And so if you wanted to answer a question like how long does it take the cop to catch the car, it's very easy to answer that graphically. We just go to the graph here and we see that at about 16.6 seconds, the car and the cop have the same that have the same position. So that is when the cop has caught up to the car. So this example shows you sort of the power of doing these animations. It makes things a little bit easier to understand in a sense, because you're getting a nice animation of the motion, and also getting these real-time graphs is pretty instructive as well. Okay, one last thing. The example in Wolfson asked a question which we haven't yet answered. One of the questions it asks is, how fast was the cop going when she passed the car? And so let's think about how we could answer that question. So here's going to be one way to do it. Instead of having our loop run for 20 seconds, let's just have it run for as long as the car is ahead of the cop. So I'm going to change the condition here for what causes the while loop to end. I'm going to say, as long as the cop has a position, x-coordinate of her position is less than the car's x-coordinate of its position, I'm going to want to make the loop run. And to actually get this to work, there's a little bit of a subtlety here. I want to make sure that the cop really starts off behind by a little bit, just by a little bit. So I'm going to make the cop's initial position here. You see I've already changed it. Instead of having the initial position to be 0, I make it 1/10 of a meter, 10 centimeters to the left. So the cop will start off behind the car and will be guaranteed that it runs through the loop appropriately. And then all we need to do to find out what the cop's position is when she catches the car is, at the very end, I'm going to add a print statement, and I'm just going to print out the value of the cop's velocity right after we've exited this while loop. And in fact, I'm going to put a little comment here in parentheses. I'm going to say the velocity of the cop when she passes the car is colon parentheses and then a comma here. So now we'll have a little printout at the end that gives us the answer that we're seeking rather. So let's run the program. Okay, and they're off. The speeding motorist is ahead, but the cop is catching up. And we expect this to go for about 16 seconds. We saw that in the last time we ran this, and there we go. The cop has caught the car, and when she did it, when she finally caught up, she was moving at 42 meters per second, which you'll notice is twice the velocity of the car's velocity. So that's probably not surprising. It took halfway through the motion. You'll notice the slope of the green curve is about the same as that of the car. So it's at about a little over 8 seconds. The cop is going at the same speed as the car. She's got to continue to accelerate, and by the time she catches up, she's going twice as fast as the car. So that is another illustration of how, just with a few minor tweaks, you can get VPython to answer questions that are of interest. So that's it for this worked example. I hope to see you again soon. Bye-bye.